Thanks, y'all. Welcome to my talk. This is called Ridiculous Radios, and this is an overview with some very specific examples of methods that I've devised to improvise radio circuits. Now, this work was done by me and also by Dominic Spill, who is not able to be here this week. So sometimes I may refer to us and our work, and we did this because a lot of this was done by Dominic and me together. So thanks to Dominic and thanks to a bunch of these other folks. I like to thank people kind of up front. So just in case I kind of run out of time at the end of the talk, I don't miss the opportunity to thank everybody who had something to do with this talk. Dominic, of course, was my research partner in putting this talk together. But all of these other people had some sort of a role in inspiring us or contributing to our work in some way, and or like helping us get a demo working. And I'll mention a few of these throughout the slides. So the things I'm about to be ashamed of are 4 radio circuits that we put together that are truly awful from a standpoint of radio engineering, but they're functional. And they can be created using components that maybe you wouldn't expect could be used to build a radio transmitter or radio receiver. They, in some cases, are made out of salvaged components. And let me give you an example. I'll just jump into my first demonstration here, my first example. Imagine this scenario: you're in the novel 1984 by George Orwell, and we found that Big Brother doesn't like us to have covert communication channels, but we found that the telescreens that are deployed by Big Brother actually have a microcontroller inside of them that has an analog to digital converter. And this is a very common component, a common peripheral to find inside a microcontroller. Now, an analog to digital converter is a device that just takes a voltage or a current and turns it into a number. And it does that many times per second. And an analog to digital converter happens to be the core component of a software-defined radio receiver. So could we build a radio receiver out of any old microcontroller that happens to have an analog to digital converter built in? And that's what we're going to try here in our first scenario. And so what I came up with is a little circuit that I call my Breadboard SDR. And I've had thoughts about making more Breadboard SDR projects, but this is the first one. And it's the simplest radio receiver that I've been able to devise that can receive radio signals that uses a general purpose microcontroller and that can receive radio signals that are much higher frequency than the speed of the analog to digital converter. The analog to digital converter on a typical microcontroller only operates at a few 100,000 samples per second, or maybe a few million samples per second. And radio signals that are useful for communicating, say at higher speeds, typically have frequencies that are much, much higher than a few megahertz. They often are a few hundreds of megahertz. So how can we build the smallest possible circuit that would allow a microcontroller to be used as a software-defined radio receiver with its built-in analog to digital converter? So here's the circuit that I came up with. Now, on the left, you see GreatFET 1, and that is a hardware hacking platform that I've designed. And in this case, there's nothing really special about the GreatFET other than that it's just a microcontroller on a USB port. It's just a general purpose microcontroller platform that I happen to like because I designed it. And the only 2 features that I'm using of this microcontroller in this circuit are the USB interface and an analog to digital converter. The analog to digital converter is sampling the radio signal, and then those samples or those measurements get streamed over the USB connection to a host computer where I can interpret that information. And you'll see on the right, there's a little breadboard, and I have two components in it. Well, actually, there are kind of three components. One of them is a resistor, one of them is a diode, and the other one is that blue wire, which is my antenna. Dominic is fond of saying that, we tuned this antenna very carefully, right? It's very important to get like the right length of wire and for the radio frequency that you're interested in. And Dominic's procedure for actually getting the right length of wire for a random wire antenna like this, it goes like this. It's very deliberate. It's very well thought out. You open the drawer, you reach in, you grab a wire, you plug it in, and if it works, you're done. If it doesn't work, you grab another wire. And this worked the first time, so we didn't have to grab another wire. It's very carefully tuned. It's it kind of goes to show that antennas, there's a lot to know about antennas if you want to make an optimal antenna, but if you want to make a functional antenna that isn't really optimal, you don't need to know a lot. You don't need to tune very precisely. You can use any old piece of wire, and it'll probably work over some distance. Just may not be as great a distance as, in theory, it could be with a better antenna. So let me show you, to explain this a little bit better, maybe, a schematic diagram. Here's a schematic diagram for this circuit. There's an antenna, there's a diode, there's a resistor, and we feed in a clock signal, which I forgot to mention earlier. That is the third feature of the microcontroller we're using here. We feed in a clock signal that is produced by the microcontroller, and it gets mixed with the signal from the antenna by that diode. And then the analog to digital converter kind of measures what the signal that's passed through the diode, that's passed through our mixer here. And the purpose of this diode, I call it a mixer because what it does is it combines the clock signal that's coming from the microcontroller with the signal from the antenna, and it produces from those two different frequencies additional frequencies. They're called mixing products, and one of those is the difference between those frequencies. So in this case, I think I was transmitting a signal in my demo that was somewhere around maybe 150 megahertz. And so I used a clock signal, a clock generated by my microcontroller at around 150 megahertz. And then that means that the signal that came in on the antenna was reduced to baseband. It was reduced to the vicinity near 0 hertz, because that was the difference of those two frequencies, the frequency over the air coming in on the antenna and the frequency of the clock, which is a radio designer would call this a local oscillator. But in my case, I was simply using a feature of the microcontroller that is a clock generator. So the microcontroller has a CPU in it. That's its main feature. And the CPU can be configured to run on a variety of different clock frequencies. It also has a couple of other parts inside that require clocks. Like, for example, the USB controller requires a clock signal. So one of the features of this microcontroller is that it has a 2 or 3 different fairly flexible clock generators inside of it. And they can operate at frequencies up to a few hundred megahertz. And it happens to have a way to actually produce an external clock output from one of those internal clock generators. So we're using its clock generator, we're using its analog to digital converter, and we're then using its USB interface to take those samples from the ADC and pump them over to a host computer. And on the host computer, what I do is I run a flow graph in GNU Radio. This is GNU Radio Companion, which is a graphical interface to GNU Radio. GNU Radio is a framework. It's for creating software-defined radio applications. And in this application, I'm sure you can't really read it from there, but you'll see there's about a dozen blocks on my screen. And basically what I'm doing is I'm taking input in the upper left-hand corner that is coming from my microcontroller, and then I'm filtering it. And down in the bottom here, I'm running it through a demodulator to actually pull information out of that radio signal. In this case, I'm pulling an audio waveform. And so when I did this demo live, I used a walkie-talkie, a fairly high-powered walkie-talkie, one that I have a license to use in the United States because I'm an amateur radio operator there. So I used a handheld amateur radio that are very commonplace as a way to create a test signal. And then and I've recorded that signal here. So this time I'm running the demo from a recording of the waveform that was captured instead of doing it live. But you can get the same results here. And here we have some audio that you should be able to hear in a moment.
Here we are testing on stage Breadboard SDR. This is AG0NR. Here we are testing on stage Breadboard SDR. This is AG0NR.
So down in the bottom, you can see a frequency domain representation and see that there is a peak that shows up in the center that doesn't exist except while my radio is keyed up. This is on a tight loop, so it only drops out for a second in between transmissions. And then on the top, you can see basically an oscilloscope plot of the audio waveform that's been decoded or demodulated from this radio signal. And it turned out this worked perfectly well. Now, one drawback of this approach is that I had to use a fairly high-powered transmitter. And the reason I had to use a fairly high-powered transmitter is because there's no amplifier in this receive circuit. It's the crudest possible circuit I've been able to devise, the fewest components. And that means it has some drawbacks, but it is functional. As long as the radio signal is strong enough, this simple circuit that can be built out of components that you might find in any electronic device can be added on to a general purpose microcontroller to produce a radio receiver that's capable of decoding, in this case, an analog audio signal, but it could be any radio signal with a maximum bandwidth described by the speed of the ADC. And it can be any radio signal up to several hundred megahertz in this case, because that's the range of my clock frequency that can be produced by the microcontroller. So the moral of the story here, the lesson to learn, is that if you build a radio in software, you don't really need much hardware. And today we have wonderful software-defined radio tools like GNU Radio that most people use with much more sophisticated platforms. Things like HackRF, for example. But if you're building your radio in software, it turns out you really don't need that much hardware. And that's one of the great things about software-defined radio, is that in software we can kind of compensate for deficiencies of our hardware. And if anyone figures out how to build a radio with fewer than 2 components, I would really like to know. Specifically a radio that has this characteristic of being able to mix down a frequency, a higher frequency to a lower one. I think there may actually be a way, but I'll save that for a future discussion. Now, here's our next scenario. And this is a transmit kind of function. I just showed you a receiver, but how do we implement transmitters if we don't have normal radio equipment or traditional radio equipment? So let's say we need to exfiltrate data from one of Big Brother's air-gapped networks. Well, we might have an ally on the inside. We might have the inside person who can help us with this, but the facility is tightly controlled, and no radio receivers or no radio transmitters are allowed inside. So can our ally reprogram a microcontroller on the inside of this network to transmit data over the air? And there are actually a lot of ways that this could be done potentially. And the most commonly implemented way is to use one of those clock signals. Just like I used a clock signal in the previous demo in my Breadboard SDR, I use a clock signal to send a signal into as a local oscillator into a mixer. We could just send that signal directly out over over an antenna. And there's been quite a bit of work done in this area already. One of my favorites is from Mike Walters, his on-off keying transmitter that I list at the top there. And one of the reasons this was a favorite of mine is because he used a GreatFET for it. And it was one of the first interesting things that anyone did with an early GreatFET. Ong Swede had an interesting talk about what he called funtennas, which are really cool. The idea being that you could take a circuit like a printer or a VoIP phone he used in one demo, and just by repurposing or reconfiguring the software on that device, turn it into a radio transmitter using by toggling signals on and off really rapidly, which are then arranging it so that those toggled signals are on connected to a wire or something that has a potential to radiate. And perhaps the most famous one is Pi FM, the Raspberry Pi FM transmitter that was implemented kind of in a similar way to what I'm about to show you by using the clock generator that's built into the Raspberry Pi's CPU. Now, one thing that we did here was we made an even simpler circuit than the previous one. In this case, we have no components whatsoever except for an antenna. So again, we use the tried and true technique of reaching into the drawer and pulling out the first wire that we found, plugging it in to the GreatFET on the pin that we expect to be toggling up and down. And we were building upon the work that Mike Walters did, where he was doing an on-off keyed transmission. So he was transmitting a signal and then stopping, and then transmitting and then stopping, and kind of like Morse code, where it's on, off, and a certain pattern. And he generated the pattern that was used by a device, an IoT light bulb that he had, or something like that. And he was able to turn on and off the light bulb just by transmitting a signal from his GreatFET. And we thought that was really cool, but we wanted to try something a little bit more ambitious. We wanted to try transmitting a frequency shift keyed transmission. So instead of having the data encoded in how the signal turns on and off, this has the data encoded in how the signal changes frequency over time. The signal wiggles between two frequencies, and when it's the high frequency, it represents a digital 1, and when it's a lower frequency, it represents a digital 0. So if you plot how the signal changes over time, or how its frequency changes over time, you'll see it's high and then low, and then high, low frequency, and low frequency. It's on the whole time. The amplitude doesn't change, but the frequency is modulated, and that carries digital information. So it's a little bit different than what Mike Walters had done, and we were playing with the PLL, which is the clock generator in the GreatFET's microcontroller. And what we determined was that we could actually use two PLLs, one to generate each frequency of our frequency shift keying, the high deviation and the low frequency deviation, and then switch back and forth between them in real time to generate a signal. So here's an example of that. You can see we have two different PLLs on the left. One of them is generating a 315 megahertz signal. The other one is generating a 315.1 megahertz signal. So those are two different clock signals running at two slightly different frequencies. And they're connected together through the SCU, which is just this basic switch box, basically. It just controls which internal signal in the microcontroller is connected to which external pin. And so in the SCU, we switch back and forth between these two different frequencies. And that is how we generate our frequency shift keyed signal that goes out over the antenna. So I'll give you a little demo here, but this is a video demo. In this video, you'll see Dominic with his laptop and a GreatFET on the hood of his car, transmitting a signal to try to get his car to do something. And you should see here, his car just unlocked. And you can see his headlights blink, and this is on a loop here, so you'll see this over and over again. He hits enter to start his program, and it transmits a signal and unlocks his car. Now, this happens to be a car that uses a remote keyless entry key fob that transmits frequency shift keyed data. And so we were able to successfully transmit this thing. And this demo was a little bit tricky to get working the first time because you have to, on a system like this, you have a rolling code. So the key fob generates a new code every time you press the button. And if you hold down the button, it should just keep transmitting that same code over and over again. But as soon as you release the button and then press it again, it generates a new code. And the car knows about this sequence of codes that it's expected. There's some kind of a cryptographic algorithm to generate those codes that both the key fob and the car know about. And if the car has seen an old code, it's no longer valid. The car expects a new code. So what we had to do to generate this demo was we had to capture a code from the key fob, but we had to do it out of range of the car. And then we had to reproduce that signal using the GreatFET in range of the car. And the first time that Dominic did this, so we went through the trouble of capturing the thing out of range of the car and then coming back to the car and getting set up. And I hadn't yet clicked record on my phone yet, and Dominic tried it. And it worked. And I said, wait, I wasn't recording yet. And he said, well, I didn't think it was going to work. And so it did work. And then we had to repeat the process, going away from the car, capturing a new code, trying it again. And here it just worked. And we learned some interesting things in the process of doing this. One of them was that we had trouble actually emulating the specific frequencies that the original transmitter used. The original transmitter had a center frequency of 315.005 megahertz. And that 0.005 may not sound like much, but realize that the frequency deviation was only plus or minus 25 kilohertz, which means it was going from 315.0 to 315.001. Those are the two frequencies that it's transmitting or jumping back and forth to encode data. And in our case, we ended up choosing a frequency deviation that was twice the deviation of the original transmitter. And we used a center frequency that was quite a bit higher than the 315.005. And the reason we ended up doing that is because we had trouble configuring our PLL as precisely as we would have liked to. And one of the PLLs we used, originally we thought we'd be able to do this with one PLL, and we tried to do that and ran into some problems. So then we tried doing it with two PLLs, and one of the PLLs we had was much less flexible in its tuning range. So we didn't have very many frequencies to choose from. So we just got somewhere near the frequency and the frequency deviation of the target device, and it worked. Which kind of goes to show that these things, these kind of low-cost digital radio receivers like the ones in your car, aren't too picky about the signals that they receive. It turns out you can actually transmit something that isn't quite exactly like the original transmitter, and in many cases, convince it that you're sending a valid signal. I want to point out, I'm going to jump back through some slides here. I want to point out that this circuit has a certain similarity to this circuit. You'll notice that the clock is connected directly to the antenna in both cases. And so, in this one where I said it was a receiver, well, guess what? It was actually transmitting too. This thing transmits as much as it receives, which is pretty ugly from the standpoint of a radio design, but it works. I'll go back past my demo. If it oscillates like a radio and emits like a radio, it's a radio, right? And it turns out that like all electronics produce radio signals unintentionally. So we're just kind of enhancing the tendency for an electronic device to produce a radio signal, taking advantage of that to turn it into a useful radio signal. And it isn't very a powerful radio signal. It doesn't work very over a very long distance, but it was effective enough to get into a car. So, third scenario, let's say Big Brother has updated the telescreens to a new version that does not have an analog to digital converter. Right? They've caught on to our little tricks and have actually just restricted the distribution of analog to digital converters in an effort to prevent improvised radio receivers. So can we use some other input, a digital input, instead of an analog input on our microcontroller to implement a radio receiver? Now, you might think that restricting analog to digital converters may be a little bit far-fetched, but it actually is something that happens in our world today. This is a page from a regulation in the United States. So this is United States law here that restricts the export of analog to digital converters that have particular characteristics. And those characteristics are, especially if you look in the upper right-hand paragraph, you can see a resolution of 10 bits or more with an output greater than 500 million words per second. That's samples per second. So what this is restricting is very high-performance analog to digital converters. And then there are different ranges of speed and resolution, how many bits an analog to digital converter uses to represent a single measurement as the resolution. So this already exists today in the world today. Countries all over the world restrict the distribution of analog to digital converters, supposedly because they have military applications, but of course they have many, many applications that are non-military. But I can definitely say that one thing they'll never be able to restrict very effectively is a digital input. They may be able to restrict analog inputs, but how do you restrict a digital input? Because every single piece of digital electronics is full of digital inputs. So, what if we could use a digital input because we don't have an analog to digital converter on our microcontroller? What if we could use a digital input to implement a radio receiver? So we put some thought into this, and we realized that we should be able to do it, we thought. But the key thing that we needed to realize was that we weren't going to get very good dynamic range. We weren't going to get going to be able to pick up very weak signals. So we needed to make sure that we had some analog circuitry in front of our 1-bit receiver that at the very least did some amplification and hopefully some filtering. And we thought, well, where could we get a circuit that has amplification and filtering and maybe mixing that we could just salvage from somewhere? Well, we found one in this metal can here that's connected to my GreatFET, this metal can is a tuner from a VCR, right? An old VCR. You might find these also in older televisions. It's a very simple radio receiver that is just the analog part. It's just the analog circuitry required to take a radio signal and pull the television signal out of it, but it doesn't actually interpret that television signal. It just shifts that, cleans it up and amplifies it and shifts it down into lower frequency range that then could be sampled by something like an analog to digital converter. So we still need the analog to digital converter here, but in this case we're using just one GPIO pin, general purpose IO pin. We're just using a digital input as an analog to digital converter instead of using a proper analog to digital converter. Here's what the circuit diagram looks like. On the right, we have the tuner, which was salvaged from an old piece of television equipment. And on the left, we have the GreatFET, which again is just our microcontroller platform of choice. Most of the connections between here are very simple. There are a bunch of power connections. We have to power up all the different power pins on the tuner. Then there are two pins that are called SCL and SDA, and those are digital control pins. Those are used just to configure the tuner. Most importantly, that turns it on and tells it what frequency we want it to tune to. And then there's this one connection that goes between the two, that bottommost connection that goes between the two parts, from the output, pin 18 on the tuner, over to a general purpose I/O pin on the GreatFET. And we put that through one component, which is a capacitor. And the purpose of the capacitor is to block DC, but allow AC, or the radio frequency, the varying part of the signal, through that capacitor. So the capacitor basically passes radio signals, even fairly low frequency ones, but it blocks DC, which is like a bias voltage. And so in this case, we wanted to make sure that we could get the GPIO pin to trigger. Now, a general purpose IO pin has some voltage threshold. You have to exceed some upper threshold in order to flip it to a 1. And then you have to drop the voltage below some lower threshold in order to flip that input to a 0. And those thresholds aren't exactly the same point. They're involved in the voltage scale. There's some distance apart, some amount of voltage that you have to exceed in order to get this bit to flip repeatedly. But those threshold voltages, as it turns out, were a lot closer together than I anticipated. And but on the other hand, they're a little bit unpredictable. You have to find the optimal threshold voltage. And so we created a DC bias by connecting actually a digital to analog converter, which is that pin on the bottom left, the DAC. We actually connected a digital to analog converter over to that GPIO signal to produce that bias voltage, produce that DC bias. And that just let us very slowly change the amount of DC seen on that GPIO pin to get us into the range of that threshold. And once we found that our bits were flipping, then we stopped modifying that DAC value. We just left it there. So that was just a way that we could tune this manually, or automatically, actually, from software. Without that DAC pin, we had to use a little resistor divider. So we had two resistors in this circuit originally to create that little bias voltage. And then I thought, well, hey, I've got this DAC here. I might as well just use that instead of this resistor divider. That reduces my circuit from 3 components down to 1 component. And it also gives me a way to automatically have software find the optimal voltage there for that bias, instead of having to determine that ahead of time and change resistors in order to reconfigure that bias voltage. Now, this tuner, in this example, we used this to capture radio signals from Dominic's key fob. So this is how we got the signal that we needed to replay in the previous demo. And so we were capturing at 315 megahertz, and the tuner takes that 315 megahertz signal and converts it down to, in this case, about 44 megahertz. This is what's called an intermediate frequency, or an IF. And we're sampling that signal with a GPIO pin that actually we were operating at less than 43 megahertz, which is kind of cool because we were doing a trick that's known as undersampling. We were sampling at a speed that was lower than the frequency we were sampling, and that works just fine, generally, with some limits, and that's a trick called undersampling. But we were also doing another trick called oversampling, and specifically oversampling and decimating. And this is the key thing to understand to know how it's possible to build a radio receiver out of a 1-bit sampler, a 1-bit ADC. So let me give you an example of this process we use called oversampling and decimation. So here's a plot of several samples. I think this is 16 samples. And each one is either a 0 or a 1, right? We're just doing a binary digital input. So every individual sample is either a 0 or a 1. And so on this plot, it's a stem plot. So there's this vertical stem below every dot. And some of the dots are way down on the 0 line, and some of the dots are up at 1. And you can see we have a bunch of random samples. Every single one is 0 or 1. Well, what if we were to take each pair of adjacent samples? So the first 2 samples we take, and we average them together. And then we take the next 2 samples and average them together, and so forth. What we would end up with is, in the first case, you can see I have a 0 and a 1, so those are going to average out to be 1/2, right? And so here's what we get if we go through that process for all 16 samples. We now have 8 samples. Some of them are 0, some of them are 1, and some of them are 0.5, right? Now we could do this again. We could take 2 adjacent samples here and average them together. And if we do that, we reduce our sample rate by half, so we have only 4 samples in the same period of time. But those samples can take on new intermediate values. They might be like 0.75, or in one case it's 1. There are more possible values here because we need more bits to represent a number. If you take like 2 8-bit numbers and add them together, you get a 9-bit number, right? You need 9 bits to represent all the possible results of that addition of 2 8-bit numbers. And the same thing we're seeing here. When we add 2 samples together, we increase our dynamic range, or we increase the number of bits per sample. We can continue this. Oops. Sorry, I don't have continued slides. We can continue this as much as we want, up to a limit of how slow we're able to make our sample rate. Because every time we divide our sample rate in half, we gain 1 bit of dynamic range. And what I'm showing you here is kind of the crudest example. In practice, what people do is not this very crude way of just averaging 2 samples at a time. They do something slightly more sophisticated where they take a bunch of information from many more than 2 samples at a time and use a low-pass filtering technique. But the end result is basically the same. You filter and decimate. Decimate means reduce the sample rate or throw out samples. Except you don't actually just discard them completely. You combine them together into a smaller number of samples that have more bits per sample. And if you do this, then you gain dynamic range. You gain the ability to discern weak signals. So you can pick up both weak signals and strong signals at the same time and differentiate them from one another and not have them interfere with one another so much, which would be a problem if we had only 1 bit per sample. So in this case, we're actually oversampling and undersampling at the same time, which sounds ridiculous, but it's truly what we're doing. We're oversampling in the sense of we're using a much higher sample rate than necessary for the bandwidth of our signal. So in the frequency domain, we're reducing the amount of bandwidth by reducing our sample rate, and that gains dynamic range. That's what oversampling is. But we're also undersampling, and that is that we are sampling at a frequency that is below that intermediate frequency of 44 megahertz. And so that's sometimes called bandpass sampling. But in this case, we're doing undersampling, or I'm calling it undersampling, because I think it's cool that it's possible to do undersampling and oversampling at the same time. So here's a little demo of our 1-bit SDR receiver. And this one is also in GNU Radio. And I think, oh, here it is. And so this is a slightly more complicated flow graph. But basically we're doing a very similar thing to what I was doing in the 1-bit SDR flow graph, in that we are trying to extract a frequency modulated transmission from this signal. And let me show you what this looks like. So here in the top, you can actually see our 1-bit samples. See how every single, that plot just jumps up and down between 2 points, because every single sample is either a 0 or a 1. So that's my raw sample stream that's coming in from my GPIO pin. And down on the bottom, you can see a frequency domain representation of that. And you can see sometimes that there are these peaks of frequency that turn up. Right there, see where my mouse is hovering over, is an interesting peak of frequency that happens from time to time. So even though we only have 1 bit per sample, the FFT, the fast Fourier transform that's producing that frequency domain view down in the bottom, is actually able to pick out some information about what frequencies are present. Now, if we decimate this signal up top, if we take that time domain signal and run it through a low-pass filter that combines a bunch of samples together, we actually get a signal that looks astonishingly good. Now, here is a version of it that is at a slower sample rate, but is, in fact, much higher dynamic range. And you see that from time to time, there's a signal present that's much higher amplitude than kind of the background noise that happens between these signals. And when you see those higher amplitude bursts, you'll see lots of little patterns that look very sinusoidal. They're very smooth. They're not these square zeros and ones. It turns out if we combine all these square zeros and ones through this process of decimating, we can get some pretty good looking radio signals. And then here's the FSK demodulation. And what this next tab is doing is it's plotting frequency on the vertical scale and time on the horizontal scale. So it's showing you how the frequency changes over time. And I have it triggering here. The triggering isn't super reliable, but from time to time you'll see it pause because it's triggering on the beginning of a signal from this key fob right there, for example. And do you see how there are periods of time where the frequency is high and then low and then high, low, high, low? That is the pattern of bits produced by the key fob when the button was pushed. And this is exactly how we were able to decode that pattern of bits from that button push, so that then we were able to replay that pattern of bits using the previous demo. So it turns out that 1 bit ought to be enough for anybody. You can make a radio receiver with only a 1-bit analog to digital converter, which can be extremely low cost and extremely available. It's something that you find on any microcontroller and on somewhere within basically any digital circuit. So in our next scenario, we imagine that Big Brother has deployed pseudo-Doppler direction finders to track down illegal radio transmitters. All right, they're finding out that they're hearing rumors that somebody is actually making illegal radio transmitters, and they're trying to find them. They're using this technique for direction finding called pseudo-Doppler direction finding. So could we steal one of their direction finding rigs and actually repurpose it as a countermeasure to prevent them from finding our signals. So this is a little bit of a weird demo perhaps, but pseudo-Doppler direction finding is a technique where you have multiple antennas. And typically, like most commonly, you'll have 4 antennas kind of in a square configuration. And then you simply have one radio receiver that rapidly switches from one antenna to the next in a cyclic pattern. So it's kind of simulating having a single antenna that's rotating very, very fast. But it's implemented by simply switching between multiple fixed antennas. Well, if you rotate an antenna very, very fast, then you actually introduce what's called a Doppler shift. You know how, like, when the ambulance is driving towards you, it sounds like a high frequency pitch, and then after it's driving away from you, it sounds like a lower frequency pitch? That's a Doppler shift. And there's a similar effect that maybe should be called Einstein shift, but there's a similar effect with radio waves and light waves as there is with sound waves. And if you have your receiver rapidly rotating, well, it goes through periods of going toward the transmitter and then going away from the transmitter, towards and away, towards and away. And so you can detect a pattern of the frequency wiggling up and down, and the phase of that wiggle changes depending on the direction of the transmitter. So this is a fairly common and well understood direction finding technique that has existed for decades. And myself and Skylar gave a talk at ShmooCon in 2018 about implementing this technique on this board that I designed called Opera Cake. This is actually an add-on for HackRF, but it's an open source hardware design that is simply an antenna switch, or really an RF port switch. You don't have to use it for antennas. But in this case, we were plugging 4 antennas into this thing and then just using the Opera Cake to switch rapidly between those antennas. Now, in this case, we wanted to produce a radio signal. So Dominic was trying to produce a radio signal that would fool my direction finder. And the way he intended to do that was by introducing a phase shift. And a phase shift is exactly what happens when my receiver is, my direction finding receiver is switching from one antenna to the next. I'm getting a little phase shift. Well, he wants to introduce phase shifts into his signal to fool my system that is actually looking for how the phase shifts over time. And what we decided to do was figure out a way to repurpose the direction finding setup, which was this Opera Cake board, and turn it into something that could change or shift the phase of the signal that he was transmitting. So this is what we did. We took a signal generator, which in this case was the cheapest 2.4 gigahertz signal generator we could find. It was a little tiny Bluetooth dongle that cost a couple of dollars. Like, this is one of the cheapest Bluetooth dongles that you could buy. It's just this tiny little USB dongle that is a Bluetooth transceiver. And it happens to be a chipset that we know how to put into a test mode. And so instead of actually transmitting a Bluetooth signal, we just had it transmitting a carrier, an unmodulated carrier in the 2.4 gigahertz band. So this is just our super cheap transmitter that we wanted it to use. We're basically repurposing a Bluetooth chip here. And so we're taking maybe a radio that we're allowed to have and then doing something we're not allowed to do with it, perhaps. And you can see we modified it a little bit. I took, on the lower right, you can see I've disconnected the internal little wiggly antenna, and instead I've added a little cable so that I can connect it to some external antenna. And then we actually connected it into our Opera Cake, which was our antenna switch. Now, this is a really sophisticated plot here that that Dominic took to designate how we actually introduce a phase shift over this signal. And the way we do it is with what's called a delay line. It takes a certain amount of time for a radio signal to be transferred from like one end of a cable to another, right? Because the speed of light is this cosmic speed limit that we can't exceed. It doesn't happen instantaneously, but it does happen very fast, that an electrical signal goes from one end of a cable to another. And if you draw kind of the sinusoid here that has the wavelength of or the period that matches the wavelength of a 2.4 gigahertz signal, which happens to be about what he's drawn there, you can see that one of the cables is slightly longer than the other one. So one of the cables is a half a wavelength longer than the other one, which means that if you were to transmit a signal over one cable, it gets through that cable slightly faster than it gets through the other cable. And what we did was we connected two of these cables using the opera cake as the switchable delay line between the Bluetooth dongle that was creating the signal and the actual transmit antenna. So we have these two different delay lines, and we switch back and forth between them. And he wrote this little program to just switch back and forth between them in a pseudo-random way, trying to fool my my direction finder. And let me show you a little demo here. So here's my very sophisticated direction finding setup with my 4 antennas in a pint glass. And I'm using GNU Radio to implement a direction finder. And now here, let me pause this for a second. Here is Dominic's transmitter. And he's seeing if he can take that tiny little blue thing in the lower left-hand corner connected to a USB cable. That's the Bluetooth dongle that he's configured to generate this test signal. It's going through the opera cake that has multiple cables of different lengths connected. He's only using 2 of those, even though he has 4 connected. And then into that transmit antenna, that little black antenna on the right-hand side of the screen. And so he's going to transmit a signal without switching its phase randomly. And you can see in the upper left-hand corner of my screen, you can see that there's this dot, this blue dot that kind of indicates the direction of that signal. I'm detecting the direction of his signal. And then he's going to turn on his script that starts randomly modulating his phase by changing that, switching back and forth between 2 different delay lines. And look what happens to my direction finding setup. Turns out this worked really well. He was able to fool my direction finding setup. I was getting useless information about what direction his signal was coming from. So adding phase shifts can actually circumvent pseudo-Doppler direction finding, which is probably one of the reasons why pseudo-Doppler direction finding isn't as popular today as it used to be, because it can be circumvented in some ways. So my last scenario here, if we can affect the phase in this way, he was able to control the output. He was able to control the phase and switch it back and forth between 2 different phases of his radio transmitter. Could he actually implement phase shift keying? That is a method of encoding information onto a signal produced by, say, this cheap Bluetooth dongle. Because if he can do that, then he can actually create a covert channel. He might have his Bluetooth dongle transmitting using frequency shift keying or on-off keying or some other technique that it maybe natively knows how to do. But then he can also add a hidden layer of modulation on top of that signal. We thought that was very interesting, and kind of a way to create a covert channel on top of a radio signal that you might be normally using or allowed to use. And so in this case, again, we were using an opera cake, in this case controlled by a GreatFET, but otherwise just an opera cake to switch back and forth between multiple delay lines. And this idea of producing covert channels by having multiple different types of modulations simultaneously is something that has existed before, most notably by Travis Goodspeed and Sergey Bratis, who did some work on, and with some other friends in some cases, on classifying different physical layer modulations, radio systems, and making what they call polyglots, which are a radio modulation that's made up of multiple modulations. So we tried this. And in this example, this is a screenshot from InSpectrum, which is a signal analysis tool that we like. And if you look down at the bottom, you actually see a plot of phase over time, and you see how the phase is kind of this sawtooth function. Most of the time, it's the phase is changing gradually at a consistent rate. It's that slope. But then from time to time, it abruptly changes. The phase abruptly changes. It jumps to another value, and then it continues gradually changing. And you can see we've lined up these cursors, these vertical dotted white lines on the screen to indicate that there are these phase shifts abruptly happening at a consistent time period. This is the first time we actually validated that we were getting those phase shifts that we wanted from Dominic's radio transmitter. So what I'm going to show you in this last little thing, I don't have a live demo of this, but I can show you a screenshot from our demo. What we decided to do was implement a phase shift keyed transmitter in the 2.4 gigahertz band. And there happens to be a very famous thing that operates in the 2.4 gigahertz band that is phase shift keyed, and it's Wi-Fi. And a lot of people don't even realize that 802.11 uses phase shift keying because they hear about all these more sophisticated modulations that 802.11 uses. But what it really uses most of the time when it's transmitting management frames like beacons and probe requests and probe responses, those things that are essential for the operation of every Wi-Fi network, it uses a modulation called DSSS, direct sequence spread spectrum. And if you really look under the hood of what direct sequence spread spectrum is, all it is just really fast phase shift keying. It's just really fast with a bunch of redundant bits in it. That's all DSSS is. And so we said, hey, if we can transmit binary phase shift keying at 11 million bits per second, we should be able to actually emulate 1 megabit per second management frames that all Wi-Fi networks use. And that's what we did. And what we were able to do was actually produce beacons to spoof that a network existed. And I was able to pick them up on my phone, and see my phone thought that there was a Wi-Fi network present. That, in fact, was simply generated by shifting back and forth between those two delay lines. So this was actually a fake Wi-Fi network produced by a Bluetooth dongle. It had no capability to transmit Wi-Fi. It was just transmitting an unmodulated test carrier, and then we were switching back and forth between two different length delay lines. And with that simple technique, we were able to improvise something that could transmit data that was seen as a Wi-Fi beacon by my phone. So an external modulator can add a covert channel onto any existing radio system, any existing radio transmitter. So thanks again to all these folks. Every single one of them here had something to do with inspiring us or helping us to achieve this talk. And thanks again to Dominic Spill for his work with me on this project. I hope you all enjoyed it, and I hope I'll see you around the con. And these are just some references because most of the code we wrote for this relied on the GreatFET project or the HackRF project, and in some cases still exists in some funny branch in one of these. But you can find me and Dominic on Twitter, or talk to me around the con if you have any questions or great ideas that you'd like to chat about. Thanks.
Thank you, Mr. Ossmann. Does anybody have questions in the audience? We'll get right to the Slido questions. How do we get to know the undersampling and oversampling rate values that will work together?
That is a tricky question for me to understand. I think so. The oversampling, really, you want to oversample by as much as you can, and the more you oversample, the better ability you'll have to discern weak signals. So there's no hard limit on how much you need to oversample. But the more you can oversample, the better. So that means you have a fairly narrowband signal of interest, but you capture with as fast a sample rate as you possibly can. Undersampling, generally, traditionally, you have a sample rate that is like higher than the frequency of interest that you're trying to capture. And in my example, I was capturing an intermediate frequency that was at 44 megahertz. And if I remember correctly, we were sampling at something like 20 megahertz. We were sampling that ADC pin, or that GPIO pin. And generally speaking, you can get away with undersampling, but only a few times your sample rate. So like, we were about half the sample rate. Our sample rate was about half the frequency of our target, and that worked okay. But if our sample rate was like 1,000th of the frequency of our target, it probably would not have worked, because the higher in frequency the target signal is relative to your ADC frequency, the limiting factor is jitter in your sample clock actually affects things worse the higher up in frequency your target is. Again, there's no hard limit. It just depends on the quality of your clock.
All right, thank you. That's our top question. So the question Hypersonic can collect his prize at the desk.
Okay.
So the next question: is it possible to use onboard network card antennas in PCs to A, exfiltrate data, B, send stealthy system commands to another machine in range, or using software to emulate missing hardware?
That is a really cool question that is a little hard to answer, because it depends a lot on the particular circumstance of the target device that you're talking about. But I really like the way that you're thinking here, which is you have a device that has an antenna built into it, like a PC of some kind that has an antenna of some kind built into it. Is there a way to repurpose that for something that it wasn't meant to be used for? In some cases, yes. An example of that, I would say, is how we were able to take this off-the-shelf Bluetooth device and get it into a test mode by telling its firmware to generate a test signal instead of telling its firmware to generate a Bluetooth packet. And so that's an example of, like, we could implement just an on-off keying transmitter using this Bluetooth device that could be embedded inside a PC. And we would be transmitting on-off key data in the 2.4 gigahertz band that would not be detected by a Bluetooth sniffer, for example, because it's not a Bluetooth modulation. So it is absolutely possible in certain cases that you could kind of, from software, reconfigure a device to produce a radio signal that is not standard, not going to be easily detected by equipment that would detect the signal that normally that device would produce. Now, if the antenna is like not connected because it has an antenna in it, but it doesn't actually have the Bluetooth chip or something like that, you probably would not have any way to control that over software, I'm guessing. And you'd be better served looking for a different funtenna, some other electrical signal, like maybe a wire that goes from the main board into a sensor, like a magnetic sensor or something around the edge of the laptop or something like that. Or an LED that's an indicator most of the time, but you could repurpose. You'd have a better luck looking for a funtenna that wasn't originally intended to be an antenna, I think.
All right, thank you very much. Please, another round of applause for Mr. Michael Ossmann.
Thank you.